Cosine, Lazan, Gillette, Lainoff.
Add a little bit of practice with the kids.
We on the air? We're on?
Yeah.
Okay. What I want to do today is finish discussing the homework 6 and then go over homework 4. And let's see, homework 6 will be due on Tuesday. And then Thursday is Thanksgiving. And then we have only 2 more meetings before the final exam. So the final exam, here's the statement about that. Exam. The exam will be Tuesday, which is the 9th. And it'll be from 4 o'clock to 6:30 in GCS 118. And that's when the exam is scheduled for the other section of this class. So it makes sense to have everybody take it together. And there's no, as far as I understand, there's no special time that's scheduled for the feeds classes. So if anybody has a problem with this time, let me know. But otherwise, the 2 sections will take it together. So any questions about anything at this point? So we're talking about homework 6, the queuing problem. And let's see where we were. I can figure out where we were. Okay, here it is, homework 6. So I think what I did last time was I gave you the basic recursion that characterizes a simulation. So we get the simulation. Let's see, let me erase this. And you have the code in front of you. It's straightforward. And it's just an implementation of this idea. Customer arrives at some time, which is random, which we call T sub n, the arrival time of the nth customer. And then when he arrives, he waits some time, which we call Wn, the waiting time of the nth customer. And then he enters service. This is for FIFO service now. So when he enters service, he spends a length of time in service called X sub n. That's his service requirement, his bandwidth requirement. And then he leaves. Now, the next customer arrives, and there are 2 possibilities. One is that the arrival time of customer n plus 1 occurs after the departure time of the customer in front of it. And that means that this customer waits 0. So in this case, his waiting time, W sub n plus 1, is equal to 0. The other possibility is that the next customer arrives before the customer who arrived ahead of him leaves. And in that case, the length of time that this customer waits is the time, the distance, or the interval between his arrival and the departure of the customer who arrived ahead of him. So when this guy leaves, the server becomes idle. Since there's service in order of arrival, FIFO service, that means that this guy will then enter service. So the length of time he waited was that minus that. So this distance right here is W sub n plus 1. So that means that the waiting time of customer number n plus 1 is equal to whatever customer number n waited, plus the amount of service for customer number n, minus their inter-arrival time. And the inter-arrival time is the distance or the time between the two customers. So IA sub n plus 1, by definition, is the time between the arrival of customer n plus 1 and the arrival of customer n. So from this diagram, you can see that this is the proper relationship. And then you see that if in fact this thing turns out negative, that's what corresponds to this case right here. So I'll indicate that by putting a plus sign around this. And what the plus sign means is you compute what's inside, and if that's negative, you replace it by 0. And if it's not negative, then you take whatever value it gives you. So all of the logic of the simulation is included right here. And that was then expressed in terms of the simulation is what? In terms of the simulation code. Statement number 120 was the one that said that that the arrival time was equal to the arrival time of the previous customer plus the inter-arrival time. And the inter-arrival time, that's drawn from earn, and that represents the inter-arrival time values, or in other words, this describes the arrival process. So this is the random process, is one of the two stochastic elements of this problem. So this tells me what the t is. Of course, in the program, I don't have the subscripts, because in the program, in BASIC anyhow, the right-hand side is the last value of the variable involved, and then the left-hand side is the newer value. Then with statement number 130, I implement this guy right here. I say that the waiting time is equal to whatever it was before plus the service time minus the inter-arrival time. So this statement is that. And then I have to take into account this plus sign here. So with statement number 140, I say that if the W that I just computed is negative, if this turned out to be a negative number, then I replace it by 0. And that's essentially it. Then later, I have to generate the service times. And those are used here. And then I go through this loop 100,000 times. Okay, so we discussed that last time. And you could actually run this now. In fact, you probably should have, even if you can't finish the problem, because I didn't finish discussing it completely last time. This is the only time you have to ask questions or have questions answered before the homework is due, which is next Tuesday. So are there any questions about the simulation, about how it works? And if you run it, it should be straightforward. It just prints out the answers. That's all there is to it. And now the objective here is to compare the simulation results with what the theory predicts and try and understand what the theory means. And it means more than just predicting the numbers, but there's a lot of insight. And so that's the important point here. I want to emphasize that this is a realistic application of probability, not just an example that's done for the purposes of illustrating the theory. Okay, so there's the simulation. You have the complete code in front of you. Of course, you don't have to do it in BASIC. You can translate to anything you want. How many people actually ran this thing? Work okay? As far as you know, I mean, you don't have formulas to check it with. All right, so the point here is that we're going to worry about two aspects. We have the inter-arrival time and the service time. This is the probability part, and this stuff really has nothing to do with probability. This is just programming logic, which translates the logic of the configuration. There's our server, and the customers arrive, and they queue up, and then they leave. So this code captures this picture. Okay, so now it says, let's go into the theory. First of all, what about the inter-arrival times? The inter-arrival times are exponentially distributed. So the times between these arrivals are supposed to be exponential, which means that the probability, as we derived in class, that an inter-arrival time exceeds t is equal to e to the minus lambda 2. where lambda is the arrival rate. And then we saw that if we translated this into a statement in terms of the inverse transform method, then we would see that the inter-arrival time is given by minus 1 over lambda. Now the lambda in our case was given as being a 1.6, or in other words, the mean time between arrivals is 5/8. So if I take 5/8, that's the average inter-arrival time, and I multiply that by the log of 1 minus a random number, that is a number that's uniform between 0 and 1, then the inter-arrival times will follow this particular property. They will have this distribution. And in the code, this is statement number 110. So what I'm asking you to do is to run this over and over again, run it for 3 different cases. In each case, we're going to have the same arrival process, which means that the arrivals occur at random, and the average time between arrivals is 5/8 of a second. Then we have to worry about the service times, and I call those X. And what we want to do is we want to compare the performance for this arrival process for 3 different service processes. And the processes are, they're given as this. The first one is exponential, and they all have an average of 1/2. So for the exponential, that means that the statement is going to be this. It's going to be minus 0.5, or 1/2, times the log of 1 minus a random number. So this statement will produce values for the service times that are exponentially distributed. In other words, they are totally random, and the average value will be 1/2 a second. Second case was where the service times are constant, and they all have the value 1/2 a second. And then I would simply say x equals 0.5. So the only difference between this and this is the amount of variability, but on the average, they're exactly the same.
That's just the inverse transform method you use in, right?
I'm using, well, in the case of a constant, the inverse transform method becomes the same as saying that the random variable equals that constant value. So in fact, in homework 3, you had exactly this. You had a constant. I don't remember it was 1/2.
Yeah.
In fact, I think it was. Okay, so that's exactly the same statement. And so is this. So there's nothing here that's new. The only thing is that now I'm using that to describe the variability in the bandwidth requirement of the individual messages. So this is a case where, in some sense, the service times are completely unpredictable, except that they have an average of 5. Here they're totally predictable, with exactly the value of 0.5. And in another case, they're sort of in the middle. That's the case of the uniform. So in that case, I would just say x equals RND, because this will produce a uniform random variable, uniform between 0 and 1, and that means that its average value is also 1/2. So this has no variability. This has large variability, relatively speaking. Not the largest possible, although this is the smallest possible. This has no variability. This has large variability, and this has variability that's in between the two. And you know that because when you looked at homework 3, you calculated the variance in each case. And you found that variance here was 0, the variance there was, what, 1/4, and the variance here was 1/12, I think. So I'm going to take those 3 cases, and I want to see what the difference is for the same arrival process in terms of the performance of the queuing model. From the simulation point of view, it doesn't matter. The simulation simply generates values this way, then this way, then this way, and gives you the answers. So what are the answers going to be? So now we want to look at the theory, because that's the interesting part. At least I claim it's interesting. I'm hoping people will find it interesting, because I'd like the people who at least feel that this course is maybe interesting will take the course in queuing theory. And as I think I gave you my website, and if you check that out, you can see some more stuff about queuing theory. And also, if you look at the website for the course, there are 2 courses listed there. One is this one, and one is the queuing theory course. And that's the queuing theory course that's taught last time. So you could download that and you could see what the assignments are, of course I'm not necessarily recommending you do that because it'll look a lot harder than it is because after all you haven't taken the course, so of course how could you do the homeworks? So it's just like this course. If you looked at the homeworks in this course before you took it, it would be much scarier than it is, I think, after having taken the course. All right, so the queuing theory course is not especially hard. In fact, I think that if you understand the stuff in this course, then the queuing theory course is actually easier because the critical point, which is understanding what randomness really is, that's covered in this course. And if you can't get that, then you don't take the other course. It's an elective. And if you do, then fine. Then you're going to see how all this works. All right, so here is what the simulation is going to print out, at least as given. So you're going to print, this is statement number 200. And you're going to print the sum of all of the service times divided by the total time simulated. So the sum of all the service times, that's all the work that the server did. So this is the total length of time that the server was busy. This is the total length of time simulated. So the ratio is the fraction of time that the server is busy. And that value is called rho in theory. So this thing right here, the name of it is the utilization. It's the utilization of the server. And it's called rho. So that's one of the measures of the performance. How busy is the server? Of course, how busy the server is going to depend on the arrival rate of the messages and the length of time required to serve each message. Okay, so we get the utilization of the server. Then there is C over 100,000. Now in the simulation, C was the total number of messages that had to wait longer than 0. In other words, it had to wait. 100,000 is the total number of customers generated, so the ratio is the fraction of arriving customers that have to wait in the queue. Or in other words, it's the probability that the waiting time is greater than 0. The fraction of customers who have to wait. So again, that's a measure of performance. The more customers that have to wait, in some sense, the worse that is. And finally, it asks you to compute, or it computes, SW over 100,000. Now, SW in the simulation is the sum of all the waiting times. So every time a waiting time is computed for an arriving customer, it's cumulated. And you add them all up, and at the end you divide the sum of all of the waiting times by the number of customers, and that gives you the average time waited by the customers. So this thing, in theory, is the expected value of the waiting time. And now the question is to see what the theory predicts and compare the simulation with the theory. Of course, the simulation is going to agree perfectly with the theory. So in that sense, you don't really have to do it. But it's interesting to see that, in fact, that works and convince yourself that this is really true. The first thing is, what's rho? Now, I'm not deriving this, although it's not a big deal to derive. Rho, remember, is the utilization of the server, or the fraction of time the server is busy. According to the theory, the way you get rho is you take the arrival rate times the average service time. And that's the answer if that value is less than 1. And the answer is 1. The utilization is 100% if that value is not less than 1. So this is the utilization. Now you can compute this. In our case, the rho is given as 1.6. 1.6 messages per second. The average service time in every case for the values we chose is 0.5 or 1/2. So that gives 0.8 or 80%. So the theoretical prediction is that when you run this simulation, the utilization of the server will be about 80%. How many people got that? Okay, so if you ran it, it's 80%, there's no question. Now, what's interesting is that the answer is 80% in each case. So what that says is it doesn't make any difference what the variability is of the stuff that you're pulling out of the urn. It's called X, the service times. It doesn't make any difference. All that matters is the average. So whether it bounces around a lot, doesn't make any difference. You're going to be busy exactly the same length of time in every case. So at first glance, that's kind of surprising. Now, actually, it's kind of two levels of surprising, because if you have never thought about probability, then people don't even think about variability. And so if they tend to think about this at all, they always consider random variables as being replaced by their average values. And if you do that, you get the right answer here, because the answer depends only on the average. Remember, lambda is an average too. It's a reciprocal of an average. And by definition, this is an average value. So that says that it's only the average values that matter, not the variability. So to someone who knows nothing, that's not surprising. But to someone who knows something, it is surprising. But if you know more than something, then it's not surprising again, because there's some insight to this, but it takes a while to develop that. So there's no reason that you should understand this. All you should say is, hey, that's kind of interesting, the fact that this answer is the same in every case. Now, the second thing is the probability of weighting greater than 0. According to the theory, that value is exactly rho. Now, that's kind of amazing, because remember that these things are measured in a completely different way. This rho, which is directly the utilization of the server, is a ratio of times. It's a ratio of the sum of all of the service times divided by the total time. So it's completely different from the way this is measured, which is a ratio of integers, because this is the number of customers who have to wait. That's the total number of customers. And at first glance, there's no reason why the fraction of customers who have to wait in the queue and the fraction of time that the server is busy are exactly the same thing. But it will turn out that they're exactly the same thing. Now, that's not always true. It's true if my arrival process is a Poisson process. But let me show you, give an example where it's not true. In fact, let's take this, the most simple-minded example that a person would take, analysis made, if he didn't know anything about the subject. So in other words, what we're going to do is, instead of looking at the arrivals and the service times as being random, let's assume that they're fixed. So now we're going to have arrivals, and we'll make the inter-arrival times exactly the average. In fact, I could simulate this by running the program with the inter-arrival times being given by a constant instead of by an exponential. Okay, now what's the inter-arrival time? Well, it's on an average 5/8, so now we're going to make all of these 5/8. Okay, so this is 5/8 seconds, and this is 5/8 seconds, and so forth. Now what about the service times? The service times are all 1/2 a second, which is 4/8. So I could draw the diagram like this. A guy arrives, and let's say that he's the first guy, so he finds the server idle, so he enters it, and he holds it for exactly 4/8 of a second. Constant. At the end of that time, he leaves. Now, when he leaves the server idle, so when the next guy arrives, which is 5/8 of a second after the previous one, the server is idle. So this guy then is not blocked. He enters service, and he stays there, again, for a constant length of time, which is 4/8. And so on. So here's the next arrival, let's say. Here's the next departure. So on like that. So every customer arrives, stays 4/8, then there's 1/8 of a second when the server is idle, then the next customer arrives, stays 4/8, then there's a 1/8 when the next customer, until the next customer arrives, and so forth. So you have all of these cycles. So in this case, what is rho going to be? Well, every cycle is the same, so you can see that every cycle the server is busy for 4/8 seconds, and the length of the cycle is 5/8 seconds. So in fact, the server is busy for a ratio 4/8 over 5/8, or I'll write it like this: 4/8 divided by 5/8, which is 4/5, or 80%. So it's exactly the utilization that we got over here. Except that here you can see it, there's no randomness whatever. Okay, so customer arrives, holds the server, goes away, next customer arrives, holds the server, goes away, and so forth. So the server is busy 80% of the time. But what's the probability of waiting? What fraction of customers have to wait in the queue? Anybody know? 0. Nobody waits, because when somebody arrives, he leaves before the next guy arrives. So therefore, nobody waits in the queue. The probability of waiting is 0. So you can see from this model that the relationship between the fraction of time that the server is busy and the fraction of customers who arrive when the server is busy, there is no relationship. Because as long as there is no blocking, as long as this time is less than that time, then the row could be anything depending on what the numbers are, and this value will always be 0. The only thing that makes the customers wait on the queue is the fact that the arrivals don't occur exactly 5/8 seconds apart, but it jiggles around a bit. And the service times aren't always exactly 4/8 of a second, but some are bigger, some are smaller. And what happens is that sometimes you get small inter-arrival times and large service times, and that's when the queues build up. So it's all because of that variability that you see the effect of queuing. So here, it turns out that, in fact, the fraction of time the server is busy and the fraction of customers who find the server busy is exactly the same thing. And when you run the simulation, you'll see that's true. But you can see from this that if you didn't have variability in it, in general, there's no relationship whatever between the fraction of time the server is busy and the fraction of customers who find the server busy. Now, it's sort of common sense that if you were an administrator for some kind of system like this and you wanted to find out what's going on in your network, you might look at your server and see whether the server is busy or not and how often it's busy. And you would naturally assume that the busier the server is, the more likely it is that there are queues, which in general is true, but not necessarily true because this example shows you that. So everything depends on the variability here. But surprisingly, the variability of the service times does not affect this answer, and it does not affect this answer. Okay, so that's surprising. I think it's surprising. Now you have to try and understand that, but that's beyond your understanding at this level. The purpose of this subject is not only to come up with formulas that are going to predict these numbers, but are going to give you insight as to what's going on, because in more complicated cases, in real engineering, the problems are usually too difficult to handle exactly theoretically, and then what you do is you have to use your engineering judgment, your intuition, your insight, which is developed from understanding those models for which you can actually compare the theory with the experiment, with the data. Okay, now there's another piece, and let me write that here. Any questions about this? So you could test this. I mean, you could run your simulation, because all you have to do is take exactly the simulation that I gave you and replace the statement that generates the inter-arrival times with the exponential with the statement that generates the inter-arrival times with a constant of 5/8. And you can see exactly. But you don't have to do it. You can see it from the diagram. Now, what about the average waiting time? So here's a formula for the average waiting time. And this is a famous formula. It's called the Pollaczek-Khinchin formula. Pollaczek and Khinchin were two mathematicians who were the first people to derive this formula, and this was done in the early 30s. I think Pollaczek published his result in 1930 and Khinchin independently in 1932. So remember, the subject began with the invention of the telephone in 1876, and then the beginning of the first commercial telephone exchange in New Haven, Connecticut in 1878. So that's when people started worrying about how you describe the behavior of these things. And then Erlang published his formulas, which are the basis. They were the first mathematical formulas, first real correct formulas for this stuff in 1917. And then Polachek and Kinchy came up with their formula in the 1930s. And this subject has been under constant development since then. So it's now about 100 years old. And if you look at the literature, you'll find that the number of papers in this area each year, instead of getting smaller and smaller because you think there's nothing left to say about a subject as simple as people arriving, waiting in line, getting served, and going away. I mean, how stupid is that? And yet the number of papers, the research is growing. It's expanding all the time. So if you go to the web and look up queuing theory, Q, something like that, you'll see literally thousands of papers. Anybody do that? Did anybody take a look at that? So take my word for it. Okay, so what is the formula for the average waiting time? It's given by rho over 1 minus rho times the average service time over 2 times 1 plus the variance of the service time distribution divided by the square of the average service time. So first of all, look how simple this formula is. Amazingly simple. You wouldn't expect that you would be able to get something so simple out of something that's so complicated. And second of all, notice that in this case, the answers are going to be different for the 3 different cases because they all have different variances. So the expected value, average value of the waiting time depends on the variability of the service times. But the fraction of time the server is busy and the fraction of customers who have to wait in the queue does not depend on that. So here you see the strange thing that this value measures the likelihood that you have to wait in the queue. This one measures how long you wait in the queue. This one depends on how variable the service times are. This one has nothing to do with the service times except for their average. So why should that be? Again, it's one of the interesting things about the subject. So what does this predict for our particular case? In our particular case, our rho is equal to 80%. The average service time is equal to 1/2. The variance varies, and the average squared is 1/4. Well, 1/2 squared. Now, 0.8 over 1 minus 0.8 is 0.8 over 0.2, which is 4. 1/2 over 2 is 1/4. So this thing, in our particular case, is 1. So I'm picking the numbers to make things as simple as possible. So for our case, the average waiting time is going to be given by the formula 1 plus 4 times the variance. Right? Have I made a mistake there, or? Okay, so what you have to do for your particular, for the homework, is you have to plug in the variance into this formula to find out what the average waiting time is. So there's going to be 3 cases. In one case, the variance is 0. In one case, the variance is 1/4, I believe, exponential. And in one case, the variance is 1/12. You plug those numbers in, run the simulation, you'll find it works. In fact, here's an interesting fact. Suppose I were to look at the case of constant service time. Let's ask it this way. What's the expected value of the waiting time for exponential service times compared to the expected value of the waiting time for constant service times? Okay, so subscript E means exponential, subscript C means constant. So now I'm going to consider the same system, the same arrival process, everything's the same average service time. Both of them have the same utilization of the server, the same fraction of customers who wait in the queue, but in this case the service times are random, in this case they're constant. What's the difference between them? Well, it's easy to see because you go back and you look at this formula here, and you see that in the case of constant service times, the variance is what? Zero. So, in both cases, this term is the same, whatever number it is. In our case, it's 1, but it doesn't matter. Whatever number it is, there's something, and that something is multiplied by 1 plus 0. If, in this case. That's supposed to be exponential service times. We got that factor multiplied by 1 plus this ratio. In the exponential case, the variance is equal to the square of the mean. That was the result that we derived in class when we calculated the mean and the variance for the exponential. So if you remember, the expected value was 1 over something, and the variance was 1 over that something squared. So what that means is that in the case of the exponential, the variance and the mean squared are exactly the same. Okay, so for exponential, the variance is equal to the square of the average. In our particular case, for the exponential, our variance is a quarter, which would make this a 1, and the constant is a 0 to make that a 0. So the point is that whatever the variance is, this ratio is always going to be 1 if the random variable x is exponentially distributed. So what does that mean? If this ratio is always 1, then the multiplying factor is 1 plus 1 or 2, which means that the average value of the waiting time in the case of exponential service times is twice as large as the average value for constant service times. In other words, there's a 100% difference. So here we have the case, if you compare the constant and the exponential, in which, in the constant case, let me say it again, you have two cases, constant and exponential, that have the same load on the server. That is, in both cases, for our argument here, we're going to consider that they have the same arrival process, the same average service time. So, in both cases, the server is busy exactly the same fraction of time, exactly the same fraction of customers wait in the queue, but if they wait in the queue, they wait twice as long in the exponential case as they do in a constant case. A 2-to-1 ratio, 100% difference. And that difference must be due solely to the variability in the service times. So there's a lot of information that's given in this formula. That's why this is such a famous formula, and why I say that the purpose of this is really insight. It's not only the fact that you want to get the answer out as a number, but you want to be able to look at this and say, what does this formula tell me? Well, one thing it tells me is that the average value of the waiting time depends on the variability of the service times. And the smallest possible variability is 0, but there is no maximum value. So that means that for any given row, for any particular given value of the fraction of time that the server is busy, no matter how small that might be, the average waiting time can be gigantic, because this value and this value aren't related to each other. So knowing how busy the server is doesn't necessarily tell you anything about how long the delays are. And the formula tells you that. It also gives you another interesting fact. This row is the utilization of the server, which has a minimum of 0, that means that nobody's there, or approaches 1 in the limit. As the utilization approaches 100%, this denominator approaches 0, and that means that the average waiting time goes to infinity. And of course, everybody already knows that. Like anybody who's been on 95, for example, during rush hour, what happens? Well, the utilization is approaching 100%, and your travel time is approaching infinity. It just stops. The whole thing becomes clogged. So, in fact, that's exactly an application of this. This is traditional, conventional in queuing theory, is that in most of these formulas that describe performance, there's a 1 minus row term in the denominator. And as the utilization of the server gets larger and larger, the performance gets worse and worse. And that's the basic dilemma, the economic dilemma, because from the viewpoint of the accountant, you want the row to be as large as possible. Because when the row is large, that means that the server is being used, so you're getting your money's worth. You're paying for the server. So you want the server to be working. You don't want to have a server that's sitting there idle most of the time. It looks like you're wasting money. But as the row gets bigger, meaning that the system gets more efficient, It's also true that this denominator gets smaller and the average waiting time gets bigger. So the engineer has to make this trade-off. What he wants to do is he wants to see what is the relationship between the utilization of the resources and the performance that the system produces. Now, for any particular configuration, the engineer can figure out what the cost is of providing that. These formulas tell him what the performance is, and then he trades off and decides how much money he's willing to spend to change the configuration to give better service. So that's the actual engineering application of these formulas. Okay, so you can see that there's a lot to this, although from the point of view of this problem, it's simple because you just run the program, see what you get, convince yourself that the theory works, and then try and understand what the theory is telling you. And in fact, on the final exam, as I say, the exam is going to relate to the homeworks. It's going to refer back to the homeworks. And when you study for it, this is an obvious place where I can ask lots of questions, because I can say, suppose that the service time distribution were such and such, then what would be the instruction that generates service times? Suppose that the arrival process were such and such. And I could ask other questions. Now, what I want to do is I'm going to ask some questions that are straightforward. In other words, you did the homework, you get the answer right. And then other questions, always one or so, that requires some insight, some thinking. And that's supposed to be something that is reasonable so that some people who have thought about this could get it, and people who haven't thought about it can't get it. So that's the purpose of it. It's to discriminate between the people who simply ran the program and people who thought about what the program does. So the way you should study for the final exam is you should take this problem and then you should say, all right, now let me look at these formulas and ask questions to myself. What would I ask if I were trying to figure out what's going on? And, well, I can't say more than that except to give you what those questions would be. But then if I do that, there's no point asking the question. What you should be doing is just saying to yourself, what is the implication of this beyond the numerical values that I get? Okay, so now there's another piece here which I haven't discussed yet, which has to do with the distribution of waiting times. So any questions about this? Yeah.
If the number of servers increase, how does that change the formula?
That's a good question. It turns out that in some cases you can get an answer in which the number of servers is an input parameter. And so therefore you have a formula and the number of servers is right in the formula and you can see exactly what the effect is. In other cases, you can't. There's actually three cases in queuing theory, in a sense, of that are of interest. One is where the number of servers is 1. That's this case. One is the number of servers is infinite, and the other is the number of servers is some finite number greater than 1. And from a mathematical point of view, the easiest case is when the number of servers is infinite. The next easiest case is when there's one server, and the hardest case is when the number of servers is more than 1 but finite. So for this particular problem, I cannot tell you, there is no simple formula for this thing, except when the service times are exponential. So that's going to get to another point now. Remember that there are basically two different things you can do with queuing theory. One is you can make the problem more or less complicated by changing the physical configuration. This is like the simplest configuration because what we have here is we've got customers arriving, queuing up, and a single server. But I could have this. Here's a typical problem. I got customers arriving to some node, let's say, and then some of them go in this direction and some of them go in that direction. And they queue up there or queue up there. And then from there, maybe they go someplace else. Could have something like that. You could have feedback. So I can make things arbitrarily complicated by having networks of queues with feedback, all kinds of things. So one complication is by making the problem physically more complicated. But another thing that I could do is I could keep something simple like this, say, but then I could change the distributions involved. For example, this formula holds if the arrival process is Poisson. Because remember, if the arrivals had constant inter-arrival times, average waiting time is 0. That was the example I showed. So the next question is, suppose that exactly this problem, but instead of assuming that I had a Poisson process for the arrivals, suppose that it was just an arbitrary process, a general process. Then what's the answer? And the answer is, well, basically we don't know. So that there are different levels of knowledge. You can always answer things by simulation, but that's only an approximation. You can often write equations and get answers by numerical analysis. That gives you numbers, and they're exact, but it doesn't give you insight. What you really want to do is you want to get formulas like this, but this is hard to do in general. So what we do is you systematically go through the cases once you understand it, where you can get formulas like this, and that gives you insight into looking at more complicated cases. And the feedback process in the learning is that you constantly are going back and forth between whatever theory you can do and what the simulation shows you. And where theory and simulation apply, that's where you gain your insight. And where in real applications, if the theory applies, you use it because that's insightful and accurate. And if it doesn't apply, then you have to go to simulation. So I'm going to give an example of that now. Okay? Question? Yeah.
You said the expected waiting time is 0 if the arrival time is constant?
Yeah, the example I gave was this. Let me go through that one more time. Suppose you knew nothing about queuing theory, and someone tells you that you have arrivals and they're occurring on average 5/8 of a second apart. So you forget the on average part, and you just say, okay, they're 5/8 of a second apart. So 5/8 of a second, 5/8 of a second, 5/8 of a second. And then you say that each arrival requires half a second for service. That's 4/8 of a second. So this guy arrives, spends 4/8 of a second, and then he leaves. And then this guy arrives, spends 4/8 of a second, and then he leaves. This guy spends 4/8, and then he leaves, and so forth. What's the utilization of the server? It's 4/8 over 5/8. Every cycle is the same. That's 80%. So the server is busy 80% of the time, but what's the average waiting time? Well, the average waiting time is 0, because this guy arrives, enters immediately, and leaves. When this guy arrives, this guy's already left. So he waits 0. He waits 0. So the fraction of customers who wait is 0, and the average waiting time is 0. Okay, now this has exactly the same row, exactly the same average service time. The only difference is that the arrival process here is assumed to be a Poisson process, that is exponential inter-arrival times, and here the inter-arrival times are constant. So the variability in the arrival process results in this formula. Whereas when there is no variability in the arrival process, and if the service times are constant, we get this.
What if the times were constant but greater than the inter-arrival time?
If I were to run my simulation with this, what I'd have for the statement about the inter-arrival times is I'd say inter-arrival time is equal to 5/8. Okay, every inter-arrival time in this urn is 5/8 of a second. And then the instruction for the service time, x is equal to 1/2. If I ran the program with those parameters, this is what I would get.
Right. But what if x was greater than 5/8?
If x was greater than 5/8, then a Q would form. And in fact, that's an interesting question. Because according to our formula for rho, remember that if lambda times E of x is greater than 1, then rho is 1. The average waiting time turns out to be infinity. The average Q length will turn out to be infinity. Of course, that's theoretical. In reality, you can't have an infinite Q. But the point is that as the rho gets bigger, then the congestion all of a sudden grows very quickly. And when you get a utilization close to 100%, everything collapses. You have gridlock. And as I say, you know that. Anybody who's ridden the 95 knows about gridlock. And you see the same thing like with a telephone system when there's a hurricane or something, or some kind of news. Everybody wants to use a telephone at the same time. Same thing with the internet. When there's a lot of spam and people put out billions of messages, then in effect what you're doing is you're increasing the lambda to the extent that the inter-arrival times are small relative to the service times, and the whole system becomes overloaded and falls apart. And mathematically what that's saying is that your rho is approaching 100%. Okay? So this formula assumes Poisson input. So if I were to run this case and then compare it with this case, for the case where the variance is equal to 0, constant service times, and I would find out that the average waiting time would be 1. So if I have Poisson input, the average waiting time is 1 second. If I have constant inter-arrival times with the same average, the average waiting time is 0. So it's the variability that causes all of the problems and all of the interest in queuing theory. Because if everybody arrived in lockstep and had exactly the service requirements, then everything would fit together exactly and there would be no problem. The problem is caused by the fact that the arrivals tend to bunch up and then space apart, and the service times tend to be some long and some short. And when you get arrivals bunching together or service times being long, then congestion results and queues build up. And then eventually they die down and the queue just fluctuates, gets bigger and smaller and bigger and smaller, as long as rho is less than 1. And if rho is not less than 1, then the queues just get bigger and everything goes to infinity and the world goes to hell in a handbasket, as they say. Okay, so apparently the exponential distribution is important, because if it isn't, and we don't have something simple like constant inter-arrival times, we don't even have a formula like this. We don't know what the answer is. So this is one of the nice things about the subject, is that from a mathematician's point of view, this is heaven on earth in the following sense. What do mathematicians like to do? They like to solve puzzles. The trouble is that who wants to pay somebody to solve puzzles? And the answer is, well, it turns out that in some cases, the solution to those puzzles really matter to practical people. Like, for example, if you're doing cryptography and you're a kid worrying about the Lone Ranger and Tonto and smoke signals, nobody's going to pay you to do that. But if you're actually breaking codes or making codes for computer systems, that can be pretty important. And there's a lot of high-powered mathematics there. People get paid for doing that. Same thing here. These are little puzzles, but it turns out that people actually care about the answers. So for someone working in this field, you have the fun of solving problems. At the same time, someone will pay you to do that because they want to know what the answer is going to be. The trouble is that often you get in a position where the people who care about the answers are very practical people, and they don't want to give you the time to do the fun stuff. They just say, "Oh, give me an approximation, write a simulation, get it over with. I got other things to worry about." So when that happens, if you work in industry, you quit and become a professor. Okay, now the statement of the problem says, at the bottom of page 1, it says, in addition, if the service times are exponentially distributed and the service is FIFO, then. Okay, so if FIFO and x is exponential, got to be careful now. It says, if this is true, then the following is true. And the following is this. The distribution function of waiting times is given by the following formula. Obviously, it's 0 if t is negative, because you can't wait a negative time. And for non-negative t, it's 1 minus rho, that's the utilization, e to the minus 1 minus rho t divided by e of x. So that's if t is not negative. So this is the theoretical distribution function. This tells you for each t, the fraction of customers whose waiting time is less than or equal to t. And you can draw its graph. Now, the derivation of this is, that's not all that bad, but one interesting fact about it is that this is if I have exponential service times. But suppose I don't have exponential service times. Then the answer is we don't know what this is. It's not, there's no simple formula for the waiting time distribution unless the service times are exponentially distributed. If the service times are constant, which would seem to be a simpler case, the resulting formula is so complicated as to not be very useful. So that's another strange thing. Why is the exponential distribution actually easier than the case in which there's no variability? And the answer is, well, it's easy to explain, but not in this course at this level. I could do it actually if I had another lecture time. Suppose you drew the graph of this. So here, and this is one of the things I'm asking you to do, to draw the graph of this. So there's t, and here is the probability that the waiting time is less than or equal to t. Now, when t is negative, it's 0. When t is not negative, it's given by this formula. So what happens when t is equal to 0? When t is equal to 0, if I plug in a 0 here, this exponential is a 1 because it's to the 0 power. So fw of t, when t is 0, is 1 minus rho, which is not 0. 1 minus rho. In other words, there's a discontinuity, a jump, and then if I was to continue to draw the graph, it would look almost like an exponential curve. It would look like that. So except for this jump at the origin, this is just like an exponential. But the jump at the origin is something you haven't seen before. This is a case of a random variable which is not discrete. W is not discrete because it's not a step function. But it's not continuous because it's not continuous. So this is in fact what's called a mixed random variable. The probability that W takes a specific value, namely 0, is 1 minus rho. But the probability that it takes any other specific value is 0. So this is not something that's made up for the purposes of illustrating that fact. This is something that is derived. This comes as a conclusion from our model. Now, what the program asks you to do is this. It says, the homework asks you to do this. Let me erase this here so I have some more room. It asks you to compute a table. And so the table is for the distribution function. So here's t, and here is the distribution function evaluated at t. And there's theory, and there's simulation. And then it asks you for t equals -1, 0, 1, 2, up to 12. So those units are now in seconds. So in other words, when I plug in -1, that's f sub w of -1, that's the fraction of customers who wait less than or equal to -1 seconds. So what's that? Well, 0, that's this branch right here. When I plug in 0, what's the value? Well, I plug it in here, it'll be 1 minus rho. In our case, rho is 80%. So it'll be 20%. So this would be 0.2. When t is equal to 1, this would be 1 minus 0.8 times this thing, where, of course, rho is 0.8, the expected value is 1/2, and the t value now would be 1. So you plug that in, you do that in the calculator, you get some number. And you do that for 2, 3. In fact, you don't want to do it with a calculator. What you should do is write a program that just puts this formula in a loop and computes it for values of t equals 0, 1, 2, and so forth. Okay, so you get all of those values, and then you plot a curve, just like you've done in all the other homeworks. Of course, it's a smooth curve, but at the particular values of t given, the curve should go through those points. And then the question is, what about the simulation? Okay, so now you're going to simulate this, which means that you have to add to the current instructions some instructions just like you did before. You have to say, for each w, every time you compute a waiting time, you say, if w is less than or equal to this value, then count it. If it's less than or equal to this value, then count it. And so on for each of these. I guess there's 14 of these, so it's kind of boring unless you put it in a loop. But in any event, for each t, you count how many times the w was less than or equal to that value, and then you divide by 100,000. And that gives you the fraction of w's that's less than or equal to that. And then you take those values, you write them in here, whatever they turn out to be, and then you put them on the curve. So for example, when t is equal to -1, your simulation, of course, is going to give you the value 0. And when t is equal to 0, it's going to give you a value which should be very close to 20%. So you get a point like maybe right here. And when t is equal to 1, well, the simulation is going to give you some value, I don't know, whatever it is, you put it there. T is equal to 2, and so forth. Now, what will happen is that you'll see that when you run this, the simulation values and the theory values are very close. In fact, when you plot it, it'll look so smooth that you'll hardly be able to know that these things are the simulation values, which of course are not exactly the same as the theory, and there's the theory, but there'll be no doubt that this is in fact the correct answer. So this formula describes completely the distribution of the waiting times if we have FIFO, service in order of arrival, and if we have Poisson input, and if we have exponential service times. But if any of those things are changed, then the curve would change. And in fact, in most cases, we don't even know what the formula would be. However, you can still simulate, because you can simulate anything. So for example, suppose I wanted to know what the answers are for the case of constant service times. I don't have a formula for that. So what I would do is I would run the program for the case of exponential service times and make sure that the theory and the simulation agree. Then I know I haven't made a mistake in my simulation. Then to go to constant service times, all I have to do is make one change. I change from x being exponential to x being constant. Run the same program, I get different answers, but I'm pretty well convinced that the numerical answers I get from the simulation will be correct because the simulation code is correct. In other words, how do you check to see whether or not the logic of your simulation is correct? In this case, you know it is because I gave it to you, and this is a simple case. But in general, simulations have complicated code. So the way you check to see it's correct is you try and run the simulation for a special case for which you know what the theoretical answer is. And then, when you get it working in that case, then you change the code slightly. That is, you change the expression that generates the values from the urn, but that doesn't affect the logic of the simulation. And whatever answers you get, well, they have to be right as long as the one instruction that generates the service times is right. All the rest of it's been checked. So that's stated here in the statement of the problem. Okay, so let me write down what you're supposed to do in the table. I'll write that over here. All right, so you've got X, the service times, and there's three cases. And then you want to calculate utilization. And you've got theory and simulation. So you already know how to do that. Then you've got the fraction of customers who have to wait. You have theory and simulation. Then it asks you for the fraction of weight greater than 1. So in the code as it stands, you didn't have that. Although, in order to do this, you had to calculate the fraction that are less than or equal to 1. So at the same time, you're calculating the fraction who are greater than 1. Because the value that's going to fit in here is just 1 minus the value that fits in here. Okay, so you take the instruction that calculates the fraction that are less than or equal to 1 and take that value and subtract it from 1, and that will give you the fraction that are greater than 1. Now, the reason I put this in here is that under case 2, I have NA and case 3. The point I'm trying to make here is that when I'm talking about values other than 0, the answer is that I have a formula, a theoretical value for this, only for the case of exponential service times. If the service times are not exponential, then I have no formula for this. So I write NA, not applicable, and I have no formula for this. However, the simulation will give me an answer, and the answer that I get here and here, they'll be different from each other, and they'll be different from that, because that depends on whatever this assumption is, and I don't have any theory for that assumption. So this is an example which shows that the way in which you actually would use simulation and theory in real life. Got to think about that, but these are the important points of the course. Then it asks you to calculate the average waiting time. And you know how to do that. Theory is the Polacek-Kitchen formula. The simulation, whatever the simulation produces. So it says, there is no simple formula for capital F sub W when the service times are not exponentially distributed. In other words, we don't know the answer for this and this. We don't have this formula except for the exponential case. Then it says, therefore, simulation is an important tool for the analysis of queues whose service time have any arbitrary specified distribution of service times. And the theoretical results for the special case of exponential service times are important because they can be used to check the logic and accuracy of the simulation. It's just like if you were writing a program to take a set of numbers and put them in order. What you would do is you would maybe run the program for a small set of numbers and then check to see whether it worked. And then if it works, you would assume that the answer does not really depend on how many numbers there are in a set. So you would run it for a large set of numbers, more than you could actually check by hand. So it's the same kind of thing here. You want to check the logic of the simulation so you compare it to the cases which is exponential, in which the theory and the simulation, for which there is theory, and if then the simulation agrees with that, then you run it for the case in which the service times are whatever you want. You don't have a theory result, but the simulation result is probably correct because the only change you made in the simulation was the one instruction that generates the service times. But the logic that describes the configuration that you're simulating, that doesn't change. Because remember, there's two pieces here. There's the descriptive piece, which is just programming, has nothing to do with probability, and then there's the probability piece, which has to do with how you specify the random variables, in this case inter-arrival times and service times, the earns from which you sample. Okay? So now you should be able to do this. It's actually very easy to do. But when you do it, you should be thinking about it. Think what it means. Try and understand it as best you can. Don't just run it, get the answers, write them down, and hand it in. I mean, that's good enough for the homework, but you don't really learn very much by doing it. You want to think as hard as you can. Because imagine that here is a question that at first glance is so simple it seems stupid. I mean, how can a grown person spend his life worrying about people waiting in line, getting served, and going away? You can't pick up many girls at a bar with that one. On the other hand, when you start thinking about it, you can see that it's really very sophisticated. And so there's a lot to this. And the thing that makes it interesting is that the mathematics is not abstract mathematics. We're not talking about bizarre things that don't have any connection to reality, but these things are closely tied to reality. So there's your intuition. Sometimes your intuition is right, sometimes it's wrong. If it were always right, then who cares? It's too easy to worry about. If it's always wrong, well, that doesn't make any sense either, because after all, this is reality. So there's this boundary of places where your intuition is wrong. You've already seen that in probability, and you want to try and change it as you go along. That's the point of education, is that your brain keeps changing in response to new insights. So let me give you one more question to think about, and we'll discuss this next time. This is one of those usual voting questions. I don't have time to vote here, but think about this. What we've looked at so far is what's called a queue. In other words, this is FIFO. But suppose we compared it with a stack. And a stack is LIFO. And here's the way the stack works. Here's my server, and suppose that there's a queue, and a customer is there. And another customer arrives. In the queue, he goes to the end. In the stack, what he does is he enters service immediately, and this guy goes to there, and that guy goes to there, and that guy goes to there. In other words, here you push the stack down when a guy arrives, and he immediately gets service. And then if he's interrupted, then he's pushed down, and everybody moves back one. But if he finishes, then he goes out, and the guy who was on the top of the stack before moves back in. So this is LIFO service, last in, first out, and it's called LIFO preemptive resume. What that means is that when a guy arrives, if somebody is in the server, that guy in the server is preempted. But when the preempted guy moves back into the server, his service time resumes from where it left off. So in other words, if this guy needs 5 seconds of service time, and he's interrupted after 2, when he comes back, he has 3 more seconds to go. Now, if you were designing a system, you could choose LIFO or FIFO, FIFO or LIFO, depending on which is better. And so that's the question I want to ask. Now, why might this be better? What's the advantage here? The advantage is that when a customer arrives, it doesn't make any difference what the queue is. He gets service immediately. So that's good. If his service time is short, then it's likely that he'll get out before somebody else interrupts him. And so therefore, guys who have short service times are going to get their service times immediately and leave. So they don't see any congestion at all. Everything is perfect for them. On the other hand, if his service time is long, then he's likely to be interrupted by a new arrival. If he's interrupted, then he goes back and he waits on the queue, and then that guy might be interrupted and so forth. So what happens here is that when I have LIFO service, I give better service to the customers whose service requirement is short, but I give worse service to the customers whose service time is long. So what's the ultimate effect? There's several possibilities. We write them down. Let's see. One is that FIFO is better. Let's see here, FIFO and LIFO. So one possibility is that the waiting times in FIFO are less than LIFO. Another is that they're greater. Another is that they're the same. Could be the same because we're talking about expected waiting times. Because what happens is the server is still going to do the same amount of work no matter how you mix them up. All FIFO and LIFO do are take different orders of the same customers. So if I mix them up, what that means is that if I give the short service time customers better service, their waiting time is less. The longer service time customers, their waiting time is more. What's the overall effect? It might be that they just exactly compensate for each other and the average is the same. It might be that FIFO has to wait longer. It might be that LIFO has to wait longer. Now, if you were designing a system, you would want to know that because that's a design decision that the person who is putting this together makes. So think about this, and I'll talk about this next time, and we'll have people vote, and then I'll tell you what the answer is.